Let's have a look at the first derivative test. It states that if c is a critical point of a function, that remember the critical point is where the derivative is 0 or not defined, then f prime of x changing from positive to negative at c means f of c is a local maximum. So let's just do sort of a chart across here about what the derivative is doing. The derivative is positive here, right? The slope is positive, the tangent line slope would be positive. It's 0 right here. It's negative between here and here, so it's negative. Then here, it's again 0. Here, it seems like it's positive for a while. Then here, it's 0 again for a while, then it becomes positive again. So if the derivative changes from positive to negative, can you see that we have a local maximum at that point? Your book goes into more detail on this theorem, but I think that's enough for the concept. What happens if the derivative changes from negative to positive? So here we're negative, then positive. Can you see that's a local minimum, right? What happens if it goes positive, 0, positive? Well, that's a critical point, but it's not much of anything. Being a critical point does not automatically make it a max or a min, okay? Let's do a few examples. This example is not precisely a book example, but you might compare it to example 4 on page 213 because it's a vertical stretch of that, and I want you to see how critical points stay, the x values of them stay unchanged even with stretches. But how do we find the critical points? First, I have to figure out what they are. Where's the derivative 0 or undefined? So 4x, oh, I'm sorry, that was supposed to be to the third. Let me pretend like it was to the third. 6x squared minus 54. Let's see, so what's that come out to? Factor out of 6, x squared minus 9, 6x minus 3, x plus 3. I wouldn't have been wrong the other way, but I was looking for something that had two critical points. X equals 3 and x equals negative 3. These are the critical points. Okay, let's analyze them with a derivative chart. Okay, so f prime of x along the number line. Now, probably what I'm going to do is I'm going to look at this version of f prime of f, although you could use this version too. Okay, so what happens if you plug in negative 3? You get 0. What happens if you plug in 3? You get 0. What happens if you plug in something really big? That's positive, so that's positive. What happens if you plug in 0? That's positive, that's negative, that's positive, that's negative. It turns out that's negative on that entire interval. And you could try that. You could plug in 1 or 2 or negative 1 or negative 2. What happens though if we plug in something smaller than negative 3? Smaller than negative 3, 6 is positive. This is negative, this is negative. Two negatives make it positive. So this is what our chart looks like. What does this mean? This means this is a critical point where the derivative goes from positive to negative. So local max at x equals negative 3. This is a place where it goes from negative 3 to positive 3. Local min at x equals 3. Some people, by the way, do their chart vertically. They say x and f prime of x. And you could do that this way also. You could say, here's negative 3, here's some value below that. You could even give it a name. You could say, okay, positive, 0, negative, or something like that. I like it horizontal because I'm used to the number line, but probably in truth, it's just because my teacher taught it to me that way to start with. Okay, let's look at the critical points of this one. What's the derivative here? F prime of x. We're going to have to use a little chain rule. So you've got the inside to the 2/5, so that's 2/5 inside to the 2/5 minus 1, so 2/5 minus 5/5 is negative 3/5 times the derivative of the inside. Well, that's just 1. So you might rewrite that as 2 over 5. Since this has a negative, it's most appropriate in the denominator, to the 3/5. Where's this going to be 0? Well, a fraction with 2 in the numerator will never be 0. But where is this going to not exist? Remember, critical points are places the derivative is 0 or doesn't exist. So there's a critical point where the denominator doesn't exist at x equals negative 2, right? That'll make the denominator 0. So let's have a look at our little chart. F prime of x is here. Let's look at the value negative 2. The derivative does not exist there. But what does this derivative do to the left and to the right? Well, pick the easiest values that you can, because it's going to be the same thing everywhere that's not a critical point. So at 0, what happens? Well, this is positive, that's positive, that's positive. What happens at, say, negative 4 or negative 100? You know, that's positive, that's positive. Negative 4 or negative 100, that's negative. Cube it, that's still negative. Take the 5th root, since those are odd, no issues at all, that's negative. What's that say if we're going down, then up? You remember down, then up, that's a local minimum. So local min at x equals negative 2. Okay, one last kind of problem that I want to chat about here, and that is, what if you have a bunch of information? You need to be able to interpret what's going on with the function. So why don't I start out by just saying, okay, let's put all of this information into order, and then below there, I'll go ahead and make a graph. This won't be the only graph, it's just a graph that has this. Okay, so what kind of information do I have? I have at 0, at negative 2, and at 3, my derivative is 0. I have my derivative doesn't exist, does not exist at 1. That could be, say, a cusp, a vertical asymptote, something like that. Let's see, my derivative, my slope is positive from negative infinity to negative 2, that's positive, and from 1 to 3, positive. And it's negative from negative 2 to 0. I think this kind of chart is just so handy in drawing these. Now what I'm going to do is I'm going to say, okay, I'm going up till here, then I'm going down till here, then I continue to go down. So this is a local max, this is a nothing. Here, I was starting to smooth out, but I shouldn't start to smooth out. The derivative doesn't exist here, so let's make it sort of a cusp. Then the derivative is going up, and then it goes back down there. So these are my 2 points that are local maxes. That's a local min, and there's a good graph for you.